Welcome to another episode of Bob Friday Talks. I am joined by Arijit Raychowdery, the Steve Chadwick School Chair at Georgia Institute of Technology. Today we're going to discuss AI in higher ed, the integration of Element, and how students practically use it in their day-to-day use today. Arijit, thanks for joining us. Maybe we can start a little bit by giving a little bit of your background, and what the research of AI looks like at Georgia Tech today.
Sure. Thanks a lot for inviting me, Bob. It's great to be here. As you have mentioned, I am currently serving as the Steve Chadwick Chair in Electrical and Computer Engineering here at Georgia Tech. I am a professor here, and I've been here for the last 11 years. This is my 12th year. Having moved here from the industry, I used to work at Intel before that, and before that, for Texas Instruments for a couple of years. So I am an industry transplant, if you may. My research interests have always evolved around circuit and circuit design, and I've, in the industry and now in academia, I've mostly been working on digital circuits. And of course, a large part of my work has also been impacted by AI. So we are using AI as in EDA tools, for example, for circuit design, as well as doing circuit design and architectural exploration for AI workloads. So you asked me about AI research in Georgia Tech. So Georgia Tech is, we are at the moment we are the largest college of engineering in the country. So you can imagine that there is a lot of work going on in Georgia Tech in the AI area, starting all the way from, if you look at just electrical and computer engineering, we have a lot of people working on new technologies for accelerating AI workloads. These are both on the server side as well as on the edge, as well as somewhere in the middle. We have people working on new transistor topologies, new integration methods, new packaging technologies, new memory technologies, new interconnects, and these involves material discovery, integration, and so on, like throughout the spectrum. And then we have people working on circuits and architecture to accelerate many of these AI workloads, including language models and vision models. And then we have people who are working purely on the theory of AI models and looking at what's there beyond deep learning, what's there beyond transformer models. How do you bring more explainability to AI models? So there's a large amount of work going on in the algorithm space in that area. And that's where engineering intersects with computer science, for example. And then on the applied side, there's a lot of work going on using AI for sustainability, for energy, for maintaining our grid. There is work going on in using AI for medical sciences, where we partner very closely with our partner institute, Emory University, which they have a medical school. There is a huge focus in robotics, particularly for manufacturing and automation. So on the applied side, of AI, you can think about all possible disciplines that's out there. Georgia Tech has some presence in any of them. So overall, I feel like we are very blessed to be in a place where there is such a vibrant research culture, and we work very closely with companies, with the government, with other entities, as we look at the entire spectrum of AI, from all the way from devices to algorithms and applications.
Yeah. So maybe, you're at the forefront of research on AI right now. We know when we look back, what happened with the internet and computers and Moore's Law, where we, doubled the size of these transistor densities every 18 months. When it comes to AI, any thoughts on how fast this AI is growing? Well, if we look at the size of these models, right, we're talking billions, if not trillions of weights. These models have gotten so large, they're on par with your brain in terms of neurons.
Yeah.
Any sense of how fast this is moving right now, towards that singularity?
So I think so let me break it down into two parts. How fast is it growing? Yeah, if you look at the model sizes, it has been an exponential growth path in the last few years, and there is I don't see any limit to this at the moment. It seems like it's just an exponent at the moment, and you can see why that's the case, right? As the models and the training data gets larger, the model sizes get larger. You are getting more and more out of these AI models. Think about language models and how better they're getting, in actually interpreting and working with humans. So that path is going to keep on continuing. But again, I think there's a realization both in the industry and academia that again that's an exponent, and all exponents eventually must die, right? Like that's the prophecy of Moore's law as well. So I think these exponents are going to not be sustainable beyond the point. There are energy crises. You would not be able to provide enough power to run these data centers or train these models. So there is to be this exponent will slow down, but what's going to come next? I think there's a large part of research that's trying to address that. What's going to happen beyond deep learning, or how do we augment deep learning with other kinds of models so that you have more, more I'd say more efficient scaling paths for AI. Then I think the question of singularity, I think I'd say that's more of a philosophical question than a scientific question. And I mean, we don't know. I think is AGI, really possible? I think maybe it is not. But at least at the moment, I feel like, we are trusting AI to do a lot more than it actually can. I think that's my worry, as opposed to, we are, AI is going to take over and kill us all. I don't think we are there, or we'll ever be there. But I'm, from my perspective, I think we need to make AI systems more interoperable. They should be more explainable. They should be more transparent. And that's how I think we'll be able to, grow a trustworthy situation with AI. I mean, the humans and AI need to work together in a trustworthy and in a secure kind of an environment. I think I feel like, we are getting there with some of the recent algorithmic advances in AI.
Maybe, from a research perspective, if you look at, what's holding back AI, do you think it's more about learning to build bigger, faster silicon and hardware to train these models? Or you think it's more about the research to be more focused on building more efficient transformer models, building newer models that are more efficiently can be trained?
That's a great question. I think there is value in both. And I am not very sure industry is the best place for doing work on let's say, larger models, more data, more training. I don't think that's something that academia is very good at. I think if you look at any of the large hyperscaler companies, superscalers, right? If you look at them, they have way more data, way more compute power, and way more resources to be able to do that kind of research. So I feel like the industry moving in that direction and bringing us more complex models from Chat GPT 4 to 5 to 6 and whatnot in one direction, and different versions of Llama and all that. So that I think is going to continue, and that's where the industry's strengths are, more data, more I'd say larger models and so on. On the academic side, I feel like more of the research needs to happen on understanding what's going on under the hood, right? Why does these models work? If we have some understanding of why the models work, we would also be able to understand when the models don't work. And that's, I think, the important part of this conversation. We also need to be cognizant of things like bias, and we need to understand, how there's training bias, there's data bias. How do we tackle some of those issues? We will also, I think, academia being the thought leader generally in social constructs, I would say you'd also play an important role in understanding how policies and regulations need to influence AI, if at all. And then there is, from a purely scientific discovery perspective, I think this whole idea of just doing deep learning is not enough. We need to augment that with with probabilistic models, with symbolic models, so we can create more holistic AI models. And there is a lot of existing data or existing understanding of how the physical world works, and our 2,500 years of physics understanding as human society and understanding of the workings of the world. That all need not be just data driven. We also need to do symbolic reasoning. So I feel like the last 40 years of AI development, not just what happened in the last 10 years, we should look at it more holistically, and that should be our driving force as far as academia is concerned.
Yeah. Well, I always wonder now, these models are getting, they're almost starting to gain the complexity of a brain. Is there any signs that the neuroscientists are going to start applying their efforts to understanding how these models work? Do you see the comparison between the brain and these big complex models starting to become a neuroscience type of problem?
Absolutely. This is a great question. I work with a group in MIT. I think they're essentially working on exactly what you're saying. So they have neuroscientists who are working on primate brains, and they're trying to understand, let's say if a rhesus monkey is looking at a bunch of different images, what parts of the brain light up, and they are trying to build deep neural network models to capture that information, and then using that deep neural network model back again in triggering some of the processes in the monkey's brain. So there is information that's going on in computational sciences that we are trying to bring back into neuroscience. And then, of course, neuroscience informs a lot of the computational models that we are developing. Having said that, I think the abstraction levels of neuroscience that we are using for computation are at a very high level. I mean, of course, the signaling at the neuroscience level is all chemical, and there are lots of processes that go on at a very low level that we really don't understand yet. But very recently, I would say that one of my colleagues in Georgia Tech, he has been applying machine learning models to understand depression in humans, and by putting something like a pacemaker, like a sensor within the brain, they were able to actually understand how to treat depression that is not typically treated by chemicals, by drugs. And they have had very good success in treating patients who have this kind of drug resistant depression by triggering right parts of the brain with electrical pulses. And the only reason that they were successful is because they have created an abstracted view of the brain
Yeah.
of the patients they're dealing with using computational models. So I think there is a lot of great synergy between both directions, like neuroscience informing computational sciences and the other way around as well, which I think is great for healthcare.
Yeah, no, it's interesting how it all started, trying to model the neural networks or model out the brain. Now we're back using them to help model the brain with these neural sciences. So,
Absolutely.
so maybe I'd like to change the topic a little bit. I'm a Georgia Tech alumni. I went to, it's been early 80s since I went to school there. Maybe give the audience a little bit of feel for how is AI really changing the student experience at Georgia Tech, at higher ed universities? Are we embracing AI as friend, foe? It kind of reminds me of the calculator in high school. Are professors embracing it as a tool to help them, or is it basically no AI in the classroom?
Yeah, great question, and I think that's a great analogy as well. And the reason I'm saying this is a great analogy is because if you talk to any student, look at any student today, no matter what campus, they are using calculators, right? So I think what has happened is, have they forgotten how to do additions and subtractions? Maybe not. I hope that they have not. They still can do additions and subtractions and multiplications and so on. But what they're also doing is they're using calculators as tools. I think that's how I look at AI, and that's why most of higher ed is looking at AI, at least in Georgia Tech. It's another tool that we have, but so you need to be able to use it properly. So Georgia Tech has completely embraced AI in all possible ways. Starting at the very beginning, when students apply for to Georgia Tech, they are now, we not only tell them that they can use AI for writing their college essays, but we actually encourage them to write their college essays with AI. So I think the idea is, you use AI as a tool, understand that it has its limitations, but if you understand its limitations and you can, provide the right prompts, for example, to a language model, you would be able to generate good text, and it will be personalized. It will be to your liking. So some generic copy and paste from an AI chat box is not what we are looking for. What we are looking for is, how do you use this better as a tool that will help you in your let's say you're writing some literary, passage, it can help you. If you are trying to understand some mathematical or scientific principle, and there is information in a trained model that can help you, I think we'll do that. The students are also, there are a couple of courses, for example, where professors are using language models to create study material for the students. It becomes more personalized, and the student is like, as opposed to having a tutor, a human tutor, you now have an AI tutor. You ask a question to this AI tutor, it replies back, and you ask another question, and so on. So I think AI, overall, I think the intersection of AI and our curriculum in Georgia Tech have been, from the very beginning, very close, and we continuously are using AI tools to evolve our curriculum and course material. So it's an ongoing process, but we are all for it, and we are kind of completely committed to making sure that our students use AI in their whatever career pursuits that they have.
Yeah. So if you had a high school senior trying to get into college and they're interested in AI, what would be the advice nowadays for someone coming into university? Is the curriculum changing? Is basically computer science the path to AI, or are they basically starting to optimize the curriculum inside the higher ed, to help a career in AI?
Yeah. I think first of all, I think your point about high school students. So just to give you some context, we feel like we need to engage with students when they're in high school and even in middle school, so that they can be well aware of what's going on in the world of engineering and sciences and AI. That will give them enough confidence that they can navigate this path, because I feel like there are a lot of students in high school who feel like they have been misinformed that AI is going to come and take all their jobs and they don't have a career path anymore and so on. So these are all, as we know, this is not the right information, right? So we want to make sure that students early on, even in high schools, are aware of what the capabilities are of AI and what AI cannot do, and where human beings are going to be important, and the jobs are probably going to evolve and change, but it's not going to be eliminated by AI. So to that effect, we have programs, for example, where we engage with local high school students, and we bring them onto campus over summer for a couple of weeks, and we teach them AI. They are using Google tools, Colab, and whatnot, and they essentially get exposed to AI tools, and they go back to their schools and teach their fellow students and so on. So there is a lot of outreach and engagement with high school and middle schools in and around the city and the state of Georgia. And then I think from the second part of the question, which was what should we tell our high school students, I think a large part of this would be computer science and algorithms is one part of AI, which is, if you really want to understand how AI works and you want to become the inventor of the next model, you have to, look under the hood and understand how AI works. You can kind of, do the math and all of that. On the other hand, AI is going to impact a whole bunch of other jobs and professions as well. And for students who are not interested in that, who want to use AI as a tool for their design project, or they want to become architects, or they want to become electrical engineers and want to use AI for essentially from a data science perspective. So we need to be able to provide them all those opportunities and those infrastructure as well, so that they can use AI for whatever educational mission that they have. So from a school's perspective, from Georgia Tech perspective, we are trying to do both. We are trying to provide opportunities for students who want to innovate the next AI model, and they are more the computer science, the electrical engineer kind of students. And then we also have students, a large number of students who would want to use AI in their individual pursuits, and we want to create a low barrier to entry for them as well. So that's going on as well.
Okay. Hey, Arijit, I want to maybe go a little bit deeper on this, your research right now, because in listening to you, it sounds like you're really working on trying to make the infrastructure more efficient in training these models, which is really about linear algebra, matrix math. Maybe give the audience a little bit of feel, how fast is that changing? How fast are we improving the compute infrastructure to actually train these models?
Sure. Of course, hardware infrastructure always moves slower than software and algorithms. Like the model sizes are increasing at alarming pace, and the hardware infrastructure is not able to keep up with it. The amount of memory that we need, the amount of compute that we need keeps on growing. Having said that, I think a large part of my research is understanding how you can efficiently map some of these algorithms, particularly the linear algebra that you need for these algorithms, on efficient hardware. A large part of the design of silicon and compute is essentially is invested in memory. Like you have large models that need to be stored in memory, and the question is, how do you move data from one part of the memory to the compute and back? And then the models are so large, you cannot fit it in one compute unit, like not one GPU, not one CPU, or one specialized accelerator that you may have. It needs to be distributed across many computes. So the question now is, how do you move data? I mean, is it copper? Is it is it going to be optical? What kind of interconnect do you need? So there are various questions that you want to answer, and I think my group is primarily interested in understanding how to use these new kinds of technologies to accelerate AI workloads of the future. And that means a lot of system level modeling and simulations, and understanding the impact of technology on these kinds of workloads. And we also build a lot of prototypes. We build FPGAs, we build GPU prototypes, as well as silicon prototypes, to test out some of the ideas that we have and kind of innovate on what's the next big compute unit beyond, let's say, a GPU that you may have, or a TPU that you may have, so that you can accelerate this huge workload exponents that you are seeing. So that's kind of in a nutshell where my research group is kind of focused at the moment.
Here at Juniper, we call that networking for AI. Where these clusters, the GPU clusters, are getting so large. As you said, it's important moving data between memory cycles, between devices and clusters and such. How important is the networking? I know at Juniper here, we're at 800 gigabits per second, right? Getting data from A to B is becoming a critical part of this. Do you see that going up to terabytes? How fast is the networking limiting how fast we can train these things?
Absolutely, network is limiting. I think if you look at some of this memory extended hardware, and if you look at some of these new kinds of protocols that we're using to send data over these links, as well as new physical layer links, right? So you're not going beyond copper, now looking at optical, and the question always is with optical the question is what's the cost? Where do what should be the length before you start going from copper to optical? There is work going on in it, even introducing optical in the package, like taking it all the way close to the chip. So I think there are different kinds of protocols, there are different kinds of physical layer mechanisms, and there are different kinds of ways that you can move and route data. So that is the big limiter at the moment. Data movement is the big limiter, because if you look at some of these AI models, the number of compute cycles per byte, that's pretty low, which means you cannot reuse a lot of the data, even if you do batching and all that. And particularly with some of these language models, you need a lot more memory per compute, or a lot less compute per byte, which means you need to move data from the memory to the logic, and from one cluster to the other, from one rack to the other. So networking will, and it still is and will continue to be a big player in how we charter our next 10 years of AI workloads in hardware. So yeah, so I'm aware of what you guys are working in Juniper, but I think the entire community that's working on the networking infrastructure, that's as vital as the companies that are building the ASICs and the hardware for the AI workloads. Yeah.
It sounds like what you're thinking on the networking side, that you think the photonics, the optics are actually going to get integrated into the chips. Is that the next big step in the networking effort to get this faster, or where do you think how fast are we going to be able to move data here? We're at 800 gigabits per second. We're going to double that next year.
Yeah, I think we will. I think we'll eventually have to go beyond 1 terabits per second. I think that's definitely the place where we want to be. I think the other important piece is what's the picojoule per bit, right? So, and I think that's another important factor. I think with optics and in the conversion, as you know, from electronics to optics and back from optics to electronics, that's expensive. So we want to make sure that we use this conversion only when needed. So there is a lot of work going on at the package level, where you want to kind of integrate optics directly on the package. But that comes with an energy cost. And a large part of the research in academia is geared towards how do you increase throughput, but also decrease energy per bit. And that involves new kinds of material. A lot of compound semiconductor work is going on in that space. And also, how do you do these conversions? This electro-optic and optoelectronic converters, and how do you build better converters so that you can integrate them very close to the logic, but at the same time make them very efficient. So yeah, this is kind of evolving, and I think there is the jury is still out. At what length scales should we introduce optics, and I think that we'll keep on working on this for the next few years for sure.
Yeah. The other topic while we have you here, I was kind of interested in was around how Georgia Tech and higher eds, because there's a lot of talk right now. Almost all the universities I work with right now are trying to come up with some AI strategy for internal operations. Maybe any words of wisdom for the other universities out there. At Georgia Tech, are you finding ways of using AI to make the university more operational efficient?
Yeah, I mean, I don't know if these are words of wisdom, but I can share some of those things that we are thinking of. We are definitely interested in using AI and AI based tools as a means of forecasting data, using it more as a data science tool. Like AI has helped us in creating dashboards, for example, where I can do very clear and easy visualization of operations of things like budget, resources, and so on and so forth. So that's one place where I've seen AI being useful. As you can imagine, Georgia Tech being such a large organization, many of the software infrastructure that we use are not developed internally within Georgia Tech. We essentially license many of these software tools, and when we license tools, I mean, many of them are already getting AI, some infusion of AI, and we are adopting many of these tools. Internally, I think we are also thinking about using AI for things like making some of our processes more better, or even for training. Like we have so many staff members that need to be trained on budget processes, on procurement processes, and so on. So there is some internal discussions and initial work going on whether we can train language models to, for example, to be very Georgia Tech specific and train people in operations. So I think that's also going on in parallel. So all of these are in very nascent stage. And again, I expect that in the next few years we'll start using this in our operations.
Maybe as we wrap it up here for the audience, any last words of wisdom where you think this this AI train is headed from a research perspective? What do you think the next major step is going to be in the journey to AI?
Yes, I think there has to be some sort of I think the energy cost of AI, particularly these language models and all, are becoming untenable. So I think that's where a lot of the investment needs to happen in making and making systems more efficient, more energy efficient. So a part of this will be in hardware, in designing data centers and making sure that we have the right kind of materials, right kind of circuit architectures, right kind of software stack to be able to make things more efficient energetically. And then I think as a society, we also need to be cognizant of the energy cost of AI. I think we enjoy making things smarter, but it comes with an energy cost. It comes with a sustainability cost. I think as a society, we need to understand that as well. So I feel like if we really want to use AI, and which we do, as a true companion, I think understanding the limitations of AI and where it is kind of consuming a lot of resources, we need to be cognizant of that. And a large part of the research, I feel like, will be driven in those directions, making things more efficient and more sustainable, as opposed to the current trend of exponential growth, which is great for the very beginning, but it's not good for long-term sustenance.
Okay. Well, I want to thank you for joining us today, and I want to thank the audience and look forward to seeing you on the next version of Bob Friday Talks.
Thank you so much, Bob. It was great talking to you. Thank you.